Students, this is Unit 2, Segment Lines and Angles, Lesson 2.4, Informal Proofs with Segments. You're looking here, friends. Make sure you get a date, time, location, as well as a parent-guardian sign-off. This page, I'd like you to do on your own using the concepts of finger segment addition. Show all your work. Remember, we're not just solving for X here, folks. We are finding everything possible. Pause the video, do your own work, then restart. Okay, welcome back. Let's see how you did here. We know we're going to do a thing equation first. There's no midpoint, so we know the segment LK plus the segment K to J is going to be the same as the distance L to J. That's called a thing equation, folks, a thing equation. So now we do circle, plug, chug. LK is 2x minus 10 plus KJ. You should have gotten 7 equals LJ. And that's going to be x plus 3. We're going to collect like terms, solve for x. X equals 6. Now, this is not algebra class. Life does not end with solving for the variable, because that's a squeeze the sponge. So we take that variable and we find everything possible. So we have 2 times 6 minus 10, that's going to be 2. And that's 7. And then this is going to be 6 plus 3, which is 9. And we check, does 2 plus 7 equal 9? Yes, check. Right here, again, things before algebra, we know the segment BC plus the segment CD equals BD. Circle, plug, chug, this is 2x plus 15. That's 8. Collect like terms, we have 2x okay, we have x equals Alrighty, so now we take that value of x and we're going to plug it in here, and 2 times negative 6 is negative 12 plus 15, that's 3. That makes this whole side, 8 plus 3 is 11. And then we check down here, if we stick a negative 3 there, or negative 6, excuse me, this whole thing will also be 11. Check. It always works when you have it correct. So that was segment addition. Now we're going to go and talk about the logic behind segments. So we're talking about something called segment proofs. Do not let that word proof intimidate you. Next to the word proof, I'd just like you to write explanation. A logical explanation. By the time we're done, you're going to be familiar with these terms: reasoning, symmetric, reflective, transitive, proof, justification. Now, the ability to use reason, logic, and justification is the foundation of all research. Research, you're trying to find the why of a system. Why does a certain disease progress the way it does? What do we do about it? In the legal setting, we're trying to answer the question, why is someone considered guilty or not guilty? And using justifications based on evidence and argumentation. You guys encounter the why quite frequently when you are writing essays. And if you're going to state a certain character has this quality, you have to support that with the why quotes from the book. So in this class, you first encountered the word why doing what's called algebraic proofs. Let's do this one together. I'm just going to quietly do the algebra here on the left. You do your own algebra, look up when you're done, see if you're the same. Please don't just copy, folks. Actually do your own algebra, look up when you're done. So you solve for the left. And so the what is the answer is -1. What is the answer? That answers the question, what? How did you get there is this work. And then the why, those properties we've learned. For example, from here to here was the distributive property. Here to here, we added, subtracted real numbers, also known as collect-like terms. From here to here, we added to both sides, so that is the addition property. Or you could have subtracted first, that's fine. From here to here, we subtraction property. Last but not least, we divided both sides, so that was division property. So the right-hand side addresses the question as why is each of these steps allowed? We're going to be doing this using segments. Before we do that, we need to get your brain warmed up. This page, I want you to take a look top to bottom, and I want you to spot as many changes as you can. Circle them, shade them, highlight them, whatever it is. I'm going to be looking for this as part of your homework, and no, I'm not going to give you the answer in the video. But paying attention to detail is what is important today. So pause the video, find as many as you can, and then restart. Welcome back. I'd like you to put the number that you found here in the corner. How many changes did you find from top to bottom? Put it right there. Now, paying attention to changes is what is super key. I need you to get out your blue reference booklet. Yes, you're actually going to do this with the video. And I highly recommend you get yourself some colors handy of some sort, at least 3 to 4, or maybe even a highlighter. I'd like you to open up your reference booklet until you see something called segment properties. Segment properties. You should be looking at this page. If you need to, pause the video and find this page. You're looking in your reference booklet. Alrighty. So we have here some of the list of the y's from previous algebraic y's. Distributive property, multiplication property, communicative property, cross multiplication property, etc. So that you're familiar with from algebra. Now we are going to give you some properties of segments. One is that segments can be what's called symmetric. So if I have this segment here, PQ, I can do this. Watch carefully. Wow, that's a tough one, folks. Segment PQ is congruent to the segment QP. That's called symmetric. Symmetric. Now the next one looks even stranger. Go ahead and label this triangle ABC. Label the midpoint there Q. Draw down the segment BQ. Now in this triangle, two separate triangles actually share the segment BQ. They share it. It's like an apartment wall. And in this case, when you say one segment is shared by exactly two other shapes, we write it like this. BQ is congruent to, drum roll, BQ. That's called reflexive, folks. Reflexive. The easiest way I can think of it is if you have a mirror and you look in the mirror. That's my attempt at an eyeball for you non-artists. And you see yourself looking back. That's why it's called a reflection. You see the same thing. So reflexive in geometry is a segment that is shared exactly by two other shapes. Let me give you another example. Go ahead and label this D, E, F, G. We have two overlapping triangles here, two overlapping triangles. Let's pull these triangles apart so that they are easy to see. You have this triangle. We're going to pull it apart here in baby form. And then you have this triangle, the green one. Pull it apart. Let's bring our letters over. Red triangle was DGF. The green triangle was EF and G. Now, if you look carefully at these two triangles, there is a segment that is exactly shared by both sides, exactly shared by both of these shapes, and that is GF. GF in the original is overlapping and shared by both triangles. That is another example of the reflexive property. So we would write it like this. GF is congruent to GF. Reflexive, again, means it's shared by two shapes. Transitive. Transitive. Above the word transitive or right next to it, write the word transfer. Get a couple colors out. This is really easy to see with colors. Let's say in this segment that HI and IJ are congruent. In other words, I is the midpoint of HJ. So H to I is congruent to I to J. Let's say J is the midpoint of IK, so that, this is also true, right, and, okay, I got some stray markings here. And let's say this is also true. That IJ is congruent to JK. Okay, look really carefully. I'd like you to circle which segment is connected to both. See how IJ is repeated? If IJ is repeated there, we can transfer congruency from HI and IJ to JK, and we can come to this conclusion. Therefore, these three little letters mean therefore, we can say that we can transfer congruency from HI to JK. That's called transitive property. Transitive property. HI is therefore now congruent to JK. Why? Because of the transitive property. We transferred congruency at IJ. That's called transitive. Another thing is important is that segments can be added. So let's offset this. Let's say we have P, Q, and R. We did this last class. So basically, little segments add up to big segments. So in this case, the red plus the blue adds up to the green. Little segments can add up to big segments. So segments can be added. Little ones add up to bigger ones. Last one, very common sense. If Q is the midpoint, then we know this. Little segments, one segment can be equal to the other. So these are all segment properties. Just like in the past we studied algebraic properties, these are what are called properties of segments. So we're going to use that just like we did proofs. Next page in your reference folder. We're still in your reference folder here, folks. This is where colors are going to come in very, very handy. I'm going to be using mostly red, green, blue, and then maybe a highlighter, okay? Now, what I'm introducing to you is something called a proof. All a proof is an explanation. Do not freak out. It's not as hard as you think it is. We're going to be following what's called the gift process. Gift. Gift. That's why there's a gift there. We're going to read the given aloud carefully and mark it on the diagram. We then mark what's implied by the given. We're going to mark what are called freebies. That's not a technical term. There's things that are true even if they're not in the diagram. An example of a freebie would be a reflexive segment. We're going to talk through connecting the given to the prove. Given, implied, freebies, talk through. This little symbol here means no naked diagrams. Your diagrams must be dressed up. Let me show you what I mean. Given. I'm going to do given in green, or the first part. We're given that the distance A to D, bracket it, I'm going to use green, is the same as the distance C to E. Again, colors are helpful. We also know that the distance B to D and DE are congruent, so BD and ED. So the greens are congruent and the blues are congruent. Now, knowing the big greens are equal and the little blues are equal, what we're going to try to prove, and prove just means explain. Don't let that word sound so official. Just explain, how do we know that AB and CD are congruent given these circumstances? Okay, so given, implied, freebies, talk through. Now, we wrote the given on the diagram. Implied and freebies, something that's implied here, we know this. We know that CE is made up of DE and CD. That's implied. We know that the big segments is made up of the little segments. Why don't we write that down for both? We also know that AD is made up of BD, the blue, plus the red, AB. That's implied. Now, knowing that, you're going to hit pause now. And I'd like you to simply actually talk it through. If this is true, explain to yourself why this must be true. It only takes about 45 seconds, but I do actually want you to talk. Pause the video, talk that through. All righty. Now that we're going to talk it through, you've talked it through, you should have said something like, oh, well, if the big segments are equal, and these little pieces are equal, if you take away the little piece, then these red pieces have to be equal. It's really not that hard. But we're going to document it here in something called a proof. It's just like you did the algebra. Before, we had algebra on the left and the y's on the right. So the how is on the left and the y is on the right. It reads like this. I know that because. Ready? Okay, let's see. We know that AD, which is the big segment, let's color code that, that's green, is made up of AB, which is the red, plus BD, which is the blue. Little segments add up to big segments. Why is that true? That's simply called segment addition. That is the property of segment addition. Let's see. Oh, CE, that's this here, that's also grain, is made up of C to D, which is the red, plus DE. Little segments add up to big segments. Why do we know that? That is called segment addition. So why can we take that step? It's the properties you just wrote on the other side of your folder. Now look very carefully. AD and CE are equal. Ask yourself, where do you find that information? Oh, looky there. It is given. Now remember that game, folks, where you had to figure out what changed, what changed, what changed? This is why we did that. Look very, very carefully. Ask yourself what changed. Let's see. I would like you to box A, B, and C, D. Just box it. Box it, right there, just like that. Now go above. Where do you see exactly that? A, B, and BD. Where do you see? Ready? Oh, box it. Looky there. Now A, B, and BD add up to AD. Box it. And look right here. Here's AD. So we took out AD and we substituted AB and BD for AD. Ready? Let me show you another one. Now, I'd like you to circle CD. Circle this. Circle. Where else do you see that? Circle. Do you see that's exactly the same thing? Look, oh, wait a minute. That equals C to E. Where else do I see CE? Oh, look what happened. We took out CE and we replaced it with what it's equal to. We took out one thing and replaced it with something equivalent. That is called substitution. Okay, then we go back and we ask, where do we find BD and DE being equal? Where do we find that? And we find that right there. It is given. I'm going to come in close. Now here, think of it just like a game. Just like a game. Take a look very carefully. Take a look between step 4 and step 6, step 4 and step 6. There is only one change only. Circle it. What change? See if you can spot it. Did you find it? AB is exactly the same. That's exactly the same. Do you see BD? Look what we did. Because we say BD and DE are equal, we can swap BD out and we can put in DE. And there's a reason why we're doing that. And what is that called? Take one thing out, put something else in. That's called substitution. Now we ask yourselves, why did we do that? Do you see now we have the exact same thing? Our target is to get AB and CD completely by itself. That's what we're trying to prove. We're trying to prove those segments are equal. Because these are equal, I can now subtract DE both sides. Just like you're clearing it. And because I subtract DE both sides, they cancel. So we are left with what our target was, AB, congruent to CD. And the way we got there was sub traction property. Ta-da! You just completed your first proof. Do not freak out. If this confused you, it is okay. You are not expected to grasp this right off the first try. Let's do 2 more together, and we will do more of these in class. Go back to your preview notes, please. Right where we left off. And we're going to do 2 more examples together. Again, we're going to follow GIFT. Do not freak out. This is easier than you think it is, I promise you. What is super important is you do not immediately try to fill in blanks. No, no, no. Do not immediately try to fill in those blanks. You must follow GIFT. So we're going to come up here. I need you to completely ignore those blanks. Get 3 colors out. I'm going to be using green, red, blue. Ready? Given. We're going to read the given and mark it on the diagram. So we are told that the segment CE is the same length as the segment D to F. Hatch mark, hatch mark. Implied and freebies. It's implied that CE is made up of CD plus DE. That's implied because little segments add up to big segments. So write that down. It's also implied down here that DF is equal to EF plus DE as well. Little segments add up to big segments. That's implied. So have yourself a little talk through. This is what we're trying to prove. We're trying to prove, and remember, prove just means explain. This is where colors come in handy. We're trying to prove if we know for a fact that the blues are equal, how do we know that the reds are equal? If we know for a fact the blues are equal, how do we know the reds are equal? A little question mark there. Ready? I actually want you to pause the video and give yourself about 30 seconds to actually talk through. If those big blue segments are equal, how do you know the red segments are equal? You're talking, you're not writing, talking. Okay, welcome back. Remember, no naked diagrams. We know that the blue segments are made up of the two red and green. And notice the red and green, they actually share the exact same green. If we take that away, we know the red's equal. So let's do this algebraically together, folks. Okay, step one. This is halfway done for us. Keep the color code going. If you have a quad pen, this is super easy. I recommend you get a quad pen. We know that CE and DF are equal. Why? It's part of the given. We know that the segment CE is made up of the segment CD, which is the red, plus DE. We know that. What do we call that? Little segments add up to bigger segments. That's called segment addition. We also know that DF, color code this, that's blue, is equal to the red segment DE. Excuse me, that's the green. DE is green, plus the red segment EF. Why is that true? That's also called segment addition. Now, ask yourself, what changed? Look really carefully. Here, we're left with the conclusion that the reds are equal. The problem is there's a step missing. So look very, very carefully and let's see what we can fit together. Kind of like looking for that Lego piece that fits two other pieces together. Watch very carefully. I'd like you to circle, please, CE. Now come up here. There's CE. I know that CE equals those two added together. Do you see DF? Box DF. Oh, there's DF again. I know DF equals those two added together. So, if these two are equal, then I know that these two must be equal. Let's write it down. I know that CD, I'm swapping out CE and I'm replacing what this is, plus DE, has to equal DF, connects right there, DE, plus EF. What did I do there? I substituted. I swapped this out and put this in. I swapped that out and put this in. That's called substitution. Now you asked, what changed from here to here? What is the only thing that changed? Look very carefully. Do you see we subtracted DE? we canceled, and we were left with this left over. Subtract both sides, that's called subtraction property, folks. Remember, how is on the left, y is on the right. You will get better at this as you do it. Don't panic. This is just a preview. Let's do one more. Stay right with me. If you need to, take a 5-minute break and come back. I don't want you tired doing this. If you need to, take a 5-minute break and come back. No naked diagrams. Let's follow GIFT. Given, implied, freebies, talk through. Okay, it is given in this case that AB, the segment, which is from here to here, is the same as the distance C to D. Hatch mark, that's given. Check, I've taken care of that. Again, I'm using red, green, blue. We also know that BD and DE are equal. So BD and DE are equal. We're trying to prove or explain, if we know the greens are equal and the blues are equal, how do we know that these larger red segments, A all the way to D, and C all the way to E, how do we know those are equal? The greens are equal and the blues are equal. How do we know that the reds are equal? Go ahead and just pause the video, talk that through for like 20 seconds. So let's see how we can explain this. We know that AB and CD are congruent. And we know that because it is given. All right, now let's see, ask ourselves, what else do we know here? What else is true? I also know that BD and DE are equal. Because it's given. Let's take a look at number 3. It says here that A to D, let's trace it so we know, that's the red, is equal to AB, which is the green, plus BD, which is the blue. We know that's true. Why? Little segments add up to bigger segments, so we're going to write segment addition. Let's do our other segment addition. So let's trace this one. We know CE also has to equal the green plus the blue, which is CD plus DE. Why do we know that? That's also called segment addition. All right. Now take a very close look. This is so important. Ask yourself this. What on earth happened in step 5? Just look at that super duper carefully and ask yourself, what was swapped out for what? I'm going to pause about 30 seconds here. See if you can't get ahead on this. What changed in 5? Let's ask ourselves, what changed in 5? Let's see. AD's the same, so that's the same. That didn't change. AD stayed exactly the same. But we took AB and we swapped it out for CD. Do you see that? And then we took BD and we swapped it out for DE. We took something out and put something in its place that was equivalent. That's called substitution. Now you ask yourself, why would I do that? Remember, our ultimate goal is to connect these two somehow, some way. That's our ultimate goal. How do we know that's our ultimate goal? That's our proof, ADCE. So what we're trying to build, if you will, we're trying to find a Lego connector piece that can connect them. Do you see in 4 and 5 now that we have the exact same expression? Look, CD, DE, see, it's exactly the same. If these are exactly the same, that means we can now swap these out and say they are the same. So now we finally have CE. The distance is equal to AD. What we're trying to prove there, AD and CE. And what we did is we used substitution. And we specifically used, wow, my pen is substitution. We specifically used lines 4 and 5 to do that. Now, if you're telling yourself, I have no clue what happened here, that is okay. We're going to do more of these in class. I highly recommend you come with a quad pen next class and a highlighter.